In this tutorial, we'll explore some simple methods for accurately animating a rolling object, such as a wheel or a ball, so that it rotates properly and doesn't slip against the ground. We'll use the graph editor, drivers, and path animation, and get acquainted with some basic mathematics. The problem in animating a rolling object is defining the proper amount of rotation in relation to the object's linear motion. The solution is quite simple if one takes a little time to understand some basic mathematical principles. If we have a unit circle of radius 1, it has a circumference of pi times the diameter, or pi times 2 times the radius, stated as 2 pi r, or in this case with a radius of 1, just 2 pi. The circumference is the arc length of one full revolution around the circle. One revolution equals 360 degrees, which expressed in radians equals 2 pi. If we were to unwind the circle to measure its circumference as a straight linear dimension, we would begin measuring at the point on the circle in contact with the ground, and roll it out until the far end of the circle is laying on the ground. During this process, the center of the circle is always directly above the point of contact with the ground. So, as we roll the circle along the ground, the center's motion describes a straight line representing the linear distance the circle has traveled. When the circle is completely unwound, we are left with two identical linear distances, one describing the distance the center of the circle has traveled, and the other the total circumference, or arc length, of the circle. Since the circumference of the circle is 2 pi, we know that the distance the circle's center point has traveled is also 2 pi. The rotation of the circle is more easily visualized with the addition of a wheel model. So, for any circle of a given radius, the distance traveled is 2 pi times the radius, or 2 pi r. This can be demonstrated by increasing the radius of the circle and unwinding it again. This results in a longer distance traveled by the center point. Notice the wheel with the smaller radius is rotating twice as much as the circle, even though they are both traveling the same distance. This relationship between linear distance and circumference can be expressed mathematically as distance traveled equals circumference times revolutions, or d equals c times big R. Expanding the circumference term, we get d equals 2 pi r times big R. What we wish to determine is the angle or radial amount the wheel rotates for any given linear distance its center point travels. So we express the equation in terms of revolutions by dividing through by the radius, which gives us d divided by r equals 2 pi times big R. Both d and r terms are linear dimensions, so the units cancel to leave a unitless value. 2 pi is the number of radians in one revolution of a circle, so we can convert that term to radians per revolution, leaving d over r equals radians per revolution times revolutions. The big R terms cancel, leaving radians as the solution. Distance divided by the radius of the circle equals the rotation of the circle in radians. To convert radians to degrees, we use the equivalency degrees equals radians times 180 over pi. So let's do some animating to see how this works in practice. If you don't have a model to practice with, you can create a sphere or a cylinder, but for simplicity, a simple circle will do. In the Object Properties bar on the right, enter 90 degrees for the X rotation, then press 1 on the number keypad to switch to front view, then the 5 key to switch to orthographic view. Enter 1 in location Z to move the circle up so it is resting on a ground level of 0. Press the number pad period key to zoom to full view. Next, let's create a simple marker on the circle to make it easier to see when it is rotating. Press the Tab key to go into edit mode and press the A key to deselect all selections. Make sure you're in vertex mode by clicking on the vertex icon in the bottom menu bar. Now select the bottom vertex at the world origin. Press E to extrude and Z to extrude in the Z-axis direction. Extrude the vertex up toward the center of the circle just far enough to create a visible line segment. Now, when the circle is rotated, it is easy to determine how far and how fast it is turning by observing the marker position. I'm going to use a pre-built model of a wheel for better visualization. To make it easier to calculate rotations, I'm going to set the angle units to radians in the Scene Units properties. My animation frame rate is 60 frames per second for a smoother screen capture, but yours can be lower. Let's start with the wheel at location x equals 0 and with a scale of 1, which in this case means the wheel has a radius of 1. Starting at frame 1, set keyframes on location x and rotation y. Zoom out the view so we can see the entire range of motion in the animation. Then move the time to the end frame, which for me is 240, and move the wheel location x to some new value like 12, and set a keyframe for that. So now, if we look at the animation, the wheel is moving but not rotating. According to our formula, rotation angle equals distance divided by radius, the rotation angle should equal the distance 12 divided by the radius 1, which results as 12. So I'll move the timeline to the end frame, then set the Y rotation to 12 and save a keyframe on that. Remember that we are rotating the wheel 12 radians, not degrees, so it is actually making almost 2 full 360-degree rotations. If I play the animation, the rotation looks perfect. It even follows the translation ease in and ease out. Now let's scale the wheel up by 2 and see what happens. When we play the animation, the wheel appears to be spinning too fast for its forward motion. According to the formula, we need to divide the distance by the new wheel radius of 2. We can easily do that by moving to the end keyframe, clicking on the Y rotation field, and entering \2 after the number value in the field. This creates an arithmetic expression that Blender automatically resolves to the proper value. Press Enter and resave the keyframe. When we replay the animation, the wheel rotates exactly as it should, with no slipping. So what happens if we have a more complicated motion with lots of different keyframes? Let's go into the graph editor and create a random movement for the wheel. Pull up on the divider at the bottom left corner of the 3D viewport to create a new panel. From the far left menu option, choose Graph Editor and make sure the view mode is set to F-curve. I'm going to add a bunch of random keyframes to the X location motion curve by selecting only that curve and pressing I for Insert, and inserting Selected Channels at Cursor. Once I have some new keyframes, I'll move them around to make a random wavy motion. Now it looks like a pretty complicated motion to try to match rotations with. But according to our formula, the rotations are simply some constant factor of the distance. the factor being the radius of the wheel. So we should be able to use the x translation curve and just scale it by the radius, or in this case, the inverse of the radius, since we are dividing. So let's go back to frame 1, select the x location curve and copy it. Then select the y rotation curve and set the cursor to the location of the first keyframe. With only the y rotation curve visible, paste the curve into that channel. Before scaling the curve, make sure the Scale Pivot Center is set to 2D Cursor in the Pivot options. Then align the timeline cursor with the first keyframe by selecting the keyframe and pressing Ctrl-G to snap the cursor to the keyframe. Reselect all keyframes by pressing the A key. Now scale the Y rotation curve by pressing SY, then 0.5 to scale by 1/2. Now, when we play back the animation, the wheel should rotate perfectly to match its lateral movement. If you plan to do lots of animation with the same object, not just one shot, it makes more sense to use drivers on the rotation. In the driver, you establish the relationship of the object's rotation to its translation using the equation we derived, and the rotation animates itself. I'll set up a driver using the wheel we just animated. First, reset the wheel scale back to 1 and set the location Z to 1 to lower it back to ground level. Next, delete the keyframes from the rotation channel by right-clicking in the Y rotation field of the properties and selecting Clear Keyframes. Right-click in the field again and choose Add Drivers, Manually Create Later, Single. The number field then turns purple to indicate it is under the control of a driver. When setting drivers, I like to use a vertical side panel next to my 3D view, providing me more space to work with lots of variables. Left-click the upper right corner of the 3D panel and drag open a new panel. Change it to a graph editor, then change the edit mode to Drivers. Press N to display the Properties panel and select the Drivers tab and drag it over the graph view. If you can't see the property controls, click on the object channel name in the channel column. The box below the Add Variable button is where the data to move the rotation channel is coming from. The object field is blank, meaning the driver currently does not have an assigned object to read from. Clicking on that will bring up a list of objects in your scene. Begin typing the name of the desired object to filter the object from the list, then select it. Next, choose the transformation channel that the wheel rotation will be reading from, in this case, the X location. In this arrangement, the driver type is set to Scripted Expression, which is what we want, since we are going to drive the channel using the math expression derived earlier. The expression needs to contain the variable representing the driving channel, which is below. Let's change the variable name to something more meaningful, like distance, meaning the distance traveled by the wheel. Now, to force the driver to properly evaluate the rotation, we just enter the variable name in the expression field. Notice the driver value below has updated to the correct value, that of the X location, and all the associated properties agree. Playing the animation, we can see the wheel appears to rotate properly, but currently it only works for a wheel scale of 1. When we change the wheel scale to anything else, 3 for instance, the rotation no longer matches. We need to include the wheel radius in the expression as we derived it earlier. For now, append the expression by typing \3 after the distance variable to divide it by the radius. Viewing the animation playback with a scale of 3 reveals a problem. The wheel is slipping slightly, which is particularly noticeable during changes in direction. If I change the variable space parameter to transform space, the wheel rotates properly with no slip. Changing the variable type to single property also works, so I can only assume there is some form of evaluation bug in the world space mode. It's probably wiser to use the single property variable type by default to avoid any potential problems or confusion. When setting up the single property variable, select the property object the same as before. To fill in the path, right-click on the property in the Location X field and select Copy Data Path. Then paste the data into the path field. You will need to append the path with .x to specify the correct axis to read from. Now the wheel rotates properly with no slipping. One problem with our current driver setup is that the wheel radius is represented by an explicit constant value, which we have copied from the wheel scale property. This is bad for two reasons. First, using a constant value in an expression forces us to go back into the driver to change the value if we ever make modifications to that property of the object later on. It's better to create a separate variable linked to that property so that it updates itself in the driver expression. Second, referencing the wheel scale as the radius variable is bad because scale is not a reliable representation of the actual size of the object. An object can be modeled to any size and still have a scale of 1, which would not be an accurate representation of its radius. There are several ways to solve this problem, but for our purposes, the simplest way would be to reference the dimension property listed just below the scale in the Properties column. Dimensions are the extent of the object's bounding box area. For a simple wheel, this would represent its total diameter in 2 dimensions. You can view the bounding box of any object by clicking on the Object Display menu on the Viewport menu bar and choosing the Bounding Box option. The bounding box dimension in either radial axis will be an accurate representation of the wheel's diameter. So in this case, the wheel diameter extends in the object's x and z dimensions. I'll create a new driver variable and reference it to the wheel's x dimension. In the driver panel, click on Add Variable. From the Property menu, choose Wheel, then copy and paste the data path from the Dimension X property field. Append the path with .x. Next, let's give it a proper variable name. Since this dimension represents the total diameter of the wheel, I'll just call it DIA for short. Now we have to include this new variable in the driver expression, so we'll replace the 3 in the expression with our new variable name. But this is still not correct. The distance must be divided by the radius, not the diameter, so we need to divide the diameter by 2. Then enclose the operation in parentheses for proper syntax and evaluation. Playing the animation, we can see the wheel still rotates properly. Now, no matter what I change the wheel scale to, the driver updates the radius automatically and continues to animate properly. There remains one other big problem with this setup. We can only animate the object along one axis. Currently, the wheel is translating along the x-axis, but if I want to turn the wheel to travel along the y-axis, I run into problems. I'll delete the keyframes on the x-axis so I can move it freely. I'll change the view to perspective and rotate the wheel around z to move it in the y-axis direction. Now if I try to move the wheel along the y-axis, it will not rotate at all. obviously, since the driver is only referencing movement in the x direction. We could set up the driver to include movement along the y-axis, but that would require a more complicated expression using trigonometry. Or we could build a complicated wheel rig, which is not the purpose of this tutorial. There is a simpler solution using path animation. Path animation is a simple and powerful method for animating a rolling object in any direction without using complicated rigging. It provides lots of flexibility for changes with minimal effort. But there is a slight catch. Remember that in order to accurately animate a rolling object, we must know the distance the object has traveled at any given moment. Following an arbitrary non-linear path presents a difficult problem in determining its total arc length. The arc length of a Bezier curve is data we do not have immediate access to in Blender without performing some relatively complicated math. Fortunately, there is a workaround. Create a Bezier curve by typing Shift-A, Curve Bezier, and rename it Path Curve. Change the view to top by typing numpad 7, then 5 for ortho view. Zoom out to make room for a large path, about 20 units or more. Hit Tab to go into Edit View. E to extrude an extra vertex, then move each vertex and control point to stretch the curve out and create a long, wavy path. Go to Front View to check that the curve is flat and level. Now tab back into Object Mode and move the curve up to 1 in location Z. To measure the curve length, I'll create a simple cone to serve as a marker along the curve. Next, lower it in Z by -1, so its apex is at the world 0. Then with the 3D cursor at world origin, go to the Object menu and choose Transform Origin to 3D Cursor. Move the cone up 1 in Z so that it is at the same position as the curve object origin. With the cone selected, apply a curve modifier with deformation axis X. Assign the Bezier path as the modifier object. The cone should snap to the beginning of the curve. Now move the cone along the path using the X location input field and slide it to the end of the curve. Zoom in close to be precise. While at the end of the curve, the X location of the cone tells us the actual length of the curve. If I modify the curve by moving any of its vertices or control points, its length changes, and I will have to adjust the cone to remeasure. We will use this data in our wheel driver to determine its rotation. I'll rename the cone Path Length. Next, we'll attach the wheel to the path. First, select the wheel and set its transforms back to their original positions, location X, Y, and Z to 0, rotation Z to 0, scale to 1, and leave the rotation Y driver as it is. Click on the Constraints tab in the Properties window, then Add Object Constraint, Follow Path. Set the constraint target to the path curve. Check on Follow Curve and set the forward axis to positive X. Last, click on Animate Path to create the evaluation time curve for the path. Now select the path curve and click on the Object Data Curve icon in the Properties panel to see the path animation parameters. Go down to the Path Animation property and make sure the checkbox is on, and open it to view the controls. the frames and evaluation time properties control the position and timing of the object along the path. Frames determines the total time frames it takes to traverse the path. I'll set mine to 239. Evaluation time is the current position of the object on the path in frames. The green color indicates it is being controlled by an animation curve, which we will use later. For now, just know that it creates a one-to-one correspondence with the timeline by default. At this point, we have the wheel following a path, but it is not rotating at all. Since the previous lesson, the wheel still has the driver assigned to its Y rotation, but as you can see from the X location property, it shows no movement. So the current driver is not receiving any translation data from the wheel. That is because the wheel's translation is being controlled by the path constraint, and its position data path is now different. We will have to construct a new driver expression and variables. Since the wheel X location is controlled by the path constraint, we have to find the distance traveled by evaluating the wheel's position on the path curve. We get the curve length from our measurement cone. If we divide that by the path duration, which is the number of path divisions in the complete motion, that will tell us the distance traveled per frame. Divide that by the wheel radius to find the amount of rotation per frame. Let's type that into the expression field for now. So the first variable in the expression is the curve length. Change the distance variable. Object is path length, data path is location.x. I'll rename the variable big L for length. Shorter variable names will make the expression more legible. Rename the DIA diameter variable to h for height. New variable, but object is different on this one. Curves are not regarded as regular objects, so we have to find the property type from the menu on the left. Choose Curve since we are reading the data from the Bezier curve path. The object menu now only lists curves in the scene. The data object is not the curve object, but the curve geometry, which is a child of the object. Remember, the object contains transformation data, while the geometry contains mesh data. You can see this relationship by opening the path object hierarchy in the outliner. So we should select the child curve of the path object. For the data path, select the curve path, then right-click on the Frames property and choose Copy Data Path. Reselect the wheel and paste the data path into the driver variable path. Rename the variable DUR for duration. Now we can begin to construct our driver expression. Length L divided by duration, that is our distance per frame, divided by the radius, which is the wheel height or diameter h, divided by 2. Enclose that in parentheses. At this point, the expression is only calculating a rotation value for the length of a single frame interval, so the wheel still will not rotate yet. We need to make it accumulative for each successive frame. We do that by multiplying by the evaluation time. Each successive frame multiplies the rotation by a higher value, causing the wheel to rotate more. Add another variable. Again, choose the curve data type. Choose the Bezier curve, select the path curve, right-click Evaluation Time, Copy Data Path. Reselect the wheel and paste data path into the driver variable. Now change the variable name to t for time. To complete the driver expression, just multiply the variable t times the rest of the expression. Now the animation should play back properly. If we want a longer or shorter animation, we simply change the frame duration in the path curve properties. So now we have a wheel rotating properly on a path, but it is quite an uninteresting motion. It moves at the same speed from start to stop and only in one direction. To alter the speed and direction of the wheel, we have to edit the path evaluation time curve in the curve editor. Pull out a new panel from the bottom of the 3D viewport. Choose Graph Editor and open the curve hierarchy to display the curve name. Then zoom out the graph view to see the full animation range. To understand the evaluation time curve, the horizontal x-axis represents the actual time of the animation, while the vertical y-axis represents the position on the path as it is divided into intervals defined by the path duration frames property. The number in the frames property is totally arbitrary and can be any positive value. The evaluation time must begin at 0 to start at the front end of the path, and equal the value of frames in the path duration to reach the end of the path. The default linear graph curve makes this happen in a one-to-one correspondence of steps per frame, but we can make it go any speed or timing we want, even make it travel in reverse. We cannot edit this default curve since it is procedurally generated, so we must first delete it and then create a new curve. First set the timeline to frame 1. Then right-click on the evaluation time property and clear keyframes. Right-click again and insert keyframe. Set the timeline to the last frame of the animation. Set the evaluation time to equal the duration frames above it, and set that keyframe. Now we have a time curve we can edit. I'll move the animation time to halfway and set a keyframe there. Then grab the end keyframe and drag it down to y equals 0. This will move the wheel halfway along the path and then reverse direction and return to the beginning of the path. I can make the wheel start at the end of the path by moving the first keyframe up to the frame's value. Now the wheel travels in the reverse direction, from end to beginning. Finally, it's possible to take control of the wheel rotation so that we can perform skids and peel-outs. To do this, we must create another parameter curve using a custom property. With the path curve still selected, scroll down the Properties window to find the Custom Properties. Open that and click the Add button to create a new property. Click the Edit button. We'll name the property Skid Spin. Give it min and max values of -10,000 and 10,000 and click OK. Right-click the number field and select Copy Data Path. This new property is going to allow us to modify the wheel rotation calculated by the driver expression. Go to the wheel driver and add a new variable. The object is again the path curve geometry. Paste the copied data path into the path field. Last, give it a variable name of capital S for skid spin. To make this work, we are going to multiply the evaluation time by a scale factor coming from the skid spin value, then add that back into the evaluation time. Let's enter that into the expression to see how it works. T plus T times big S, then enclose it all in parentheses. Next, we have to create an animation curve for the skid spin property. Select the path curve, set the skid spin value to 0, then right-click on the value and insert keyframe. We should now see the new property in the graph editor. Playing the animation reveals no added effect to the wheel's rotation. That is because we are currently multiplying the evaluation time by 0 and adding that back into it, thus not changing it at all. Let's create a skid to stop at the end of the curve. I'll move the keyframe we created to 60 frames before the end of the animation. Then, a few frames later, I'll add another keyframe and set its value to -1. It's that easy. Multiplying the evaluation time by -1, then adding it back into itself, negates any cumulative effect on the evaluation time. Its output value for the rotation remains the same, even though it is still updating the wheel translation on the path. Now let's bring the wheel to a stop midway, then peel out. To stop the wheel motion, we simply create a flat section in the evaluation time graph. I'll select the middle keyframe on the evaluation time graph and set it to frame 80 and position 141. Then insert another keyframe and set it to frame 128 and position 141. Last, reselect the previous keyframe and set its control handles to auto-clamped to flatten out the curve. On the skid spin graph, insert a keyframe midway through the wheel hold section and give it a value of 0. Insert another keyframe past the point where the wheel starts moving again and set it to frame 144 and its value to 0. Then insert one more a few frames after the restart frame at 140. Set it to a small negative value between 0 and -1, like -0.4. You will have to play around with the keyframe timing and values to get the effect just right. So there are a few methods for animating wheel motion and modifying path animation. Hopefully, it will provide you with some ideas and inspire you to create more complex and interesting animations of your own. Thanks for watching.